Physics Online with your teacher. That's me. All right, so we're going to talk about Newton's second law today, and we're going to break down how we derived it, where it comes from, and some ways that we can use it. So, first of all, Newton's second law is often referred to as F equals ma. Obviously, it's a math equation, so you might see different arrangements of it. But let's talk about where this thing comes from. Well, we did an experiment in class where we graphed two variables. We graphed force versus acceleration. Now, we weren't actually graphing force, we were actually graphing a net force, which is the sum of all the forces acting on a system. Because we did the pulley experiment, where we had an object hang off a cliff with a pulley, and we had a little object here. Look at my drawing skills. All those years, they've really paid off. We had masses hanging off of here, and then they were attached by a rope to a hanging mass that accelerated the whole system. And we measured that acceleration, and we looked at the force affecting the system, and we assumed that the only force was the force of gravity, so that was our net force acting on the system. The rest was normals and things like that. We assumed there was no friction, so therefore everything else balanced out. So it was just this net force. So we basically said, hey, let's calculate the force of gravity acting on our system. We'll set that equal to the acceleration of our system, but in reality, that force of gravity was the net force because we had no other forces acting on it. If we calculated the force of friction going against it in this direction here, then we would have had to add those two forces together, or in reality, subtract friction because it'd be a negative force. Anyways, that's what we did in class. What we discovered, though, is that this had a nice, pretty straight line. So we had to ask ourselves, well, what does that mean? So we just had to figure out what's the slope mean, things like that. Well, I ran this experiment myself, and the data that I collected was this. I got a slope value of, let's see, if I did 2.105 newtons per meter per second squared. My math teacher would hate me if they saw that. And a y-intercept of 0.003 newtons. So you have to ask yourself, what's this mean? Well, fundamentally, the y-intercept tells us the initial y. So it's what y is when x is 0. So it's the net force when the acceleration is 0. Well, as we learned, if you are not going to accelerate an object, you need to have constant velocity. So you have to have balanced forces. Balanced forces mean there is no net force. The net force is 0. That was the entire previous unit. So this entire y-intercept value here, I'll change my color on this. All right, this should be 0 because if this is true, all right, if the net force equals 0, then we have balanced forces and no acceleration. All right, like I said, previous unit, we learned that. So it makes sense that this value should be 0. Mathematically, it's very close to 0, so it makes sense. It all pans out, so I'm going to nuke it from my equation. Then, if we look at our slope value, different color. All right, this is something constant. Something constant that we believe is going to affect our results. Well, the only thing constant that we thought would be a factor was the mass of our system. I mean, it makes sense, you know? Big system, a lot of mass, hard to accelerate with the same force. All right, you poke me, I'm a large person. I'm not exactly going to move. I poke my small children, they collapse, mostly because they're giggling because they think I'm tickling them, but that's a whole different story. So, mass is definitely a factor. All right, so let's look at these units then. These units look nothing like mass at all. They're some of the ugliest units I've ever seen. But let me show you something. We never explained, remember I said a Newton was units, what we called the units for force because, Newton was a cool guy, did some work in the field. But those aren't the actual units. We gave them a name. The actual units for force are this: kilogram meters per second squared. And if we then divide this by meters per second squared, you might notice that some stuff is going to go away. This meters per second squared is going to cancel out with that meters per second squared, leaving us with only kilograms as our units. So in fact, the units of our slope are kilograms. So that matches the hypothesis that the only thing we kept constant was the mass, and so the slope is something constant. That was true. Also, if we look at my slope value here, I included all the masses. This number right here is very close to the mass of the system. Because remember, I had the cart, which was 500 grams. The plastic piece was 150 grams. So right there, you're at 0.65 kilograms. And then we had all the masses inside of it. And for when I did mine, it was pretty close to 2,100 because I included the 1 kilogram mass, which I said you shouldn't do. But, I'm a rebel. If you did not, then you probably found a slope that's closer to about 1.1, 1.2, somewhere in there, depending on what masses you had involved. But either way, should be pretty close to the mass the system wrote down. So what this means is we are left with our equation of y equals mx plus b, where y is our net force, the slope we've determined is the mass, the x is our acceleration, the b is 0, so we are left with this equation, which should look disturbingly familiar to the previous equation that we had. So, before we said, well, if we sum the forces, they equal 0. Well, now we're saying if you sum the forces, they equal mass times acceleration. Why'd they equal 0 before? Because before we had no acceleration. So therefore, this was a 0. Multiply anything by 0, you get 0. So the equation that we're using now is the same equation we used before. I know, it's like I tried to set you guys up for this. All right? So no major changes here. All we're saying is now we're going to be multiplying mass times acceleration. So I'll just write this out. So what this really says is the net force acting on the system equals the mass of the system times the acceleration of the system. Now notice how I keep using the word the system, because you can define whatever you want as your system. If I was to go back to my previous scenario, I could say, well, I'm just going to analyze this guy. He's my system. Or I could say, I'm going to analyze this guy. He's my system. Or I could say, I'm going to analyze everything. It's my system. You get to pick your system. So, just like before, it is incredibly important that you clearly define your system, because that's going to tell you what the mass of that system is. Then you're going to ask yourself, well, what's the net forces acting on the system? So you're going to get rid of any internal forces, things like that. But fundamentally, you're doing the exact same stuff that we did before. So all you're doing is you're now making it equal to equals ma. All right, and that is Newton's second law, that the net force acting on a system is equal to the mass of the system times the acceleration of the system. And just in case you didn't see it big enough, and I haven't used the color green, this is our new fundamental equation that we're going to start everything off with. All right. So hopefully get you started. If you have any questions, let me know, and I'll catch you on the flip side.